Math 2414, Differential Equations, Video 4, Graphs of Solutions. And you probably immediately notice that I'm not on the screen, I'm not in the view of the camera, and I'm not writing on the whiteboard. That's because what I'm about to show you is going to be much easier to use technology. I'll go ahead and get on the screen for a second. And so we're going to go to one of my favorite graphing websites. I'm not sure if the address is visible on the camera, but it's desmos.com, DESMOS.com. And if you go there, you'll see the screen. Many of you probably are familiar with Desmos. It's a free online graphing calculator, but it actually does a lot more. If you want to get your math nerd on, I recommend going to this site and just browsing. But we're going to go to the graphing calculator because this is such a sweet graphing calculator. Because you can type any equation and it will instantly graph it. For example, if I type x, it's assuming I'm saying y equals x, or type x squared minus y squared. Now it doesn't know what to do until I put an equation equals 1. I would get what's called a hyperbola. I'm going to check the view real quick to make sure that this is visible. That seems pretty good. So what am I using this for? I want to show you the solutions to some of the differential equations that we had in the previous two videos. So if you haven't watched them yet, I invite you to go back and watch the previous two videos. I'm going to start with the one that said dy dx equals x squared over y squared, and the solution we got to that was y equals the cube root. Give me a second to bring up the cube root. Let's see if I have more options here. Functions, miscellaneous, and third. There we go. I know I can just use a 1/3 power. Cube root of x cubed plus c. Now, it doesn't know what to do with the plus c, and we can do what's called adding a slider. And when you add a slider in Desmos, it says, all right, I'll let you put a letter here, and down here you tell me what the letter equals. Right now it says c is equal to 1. But the reason it's called a slider is that if you animate it, then it changes the values of that c and sketches the graph accordingly. So we see something like this. So here's when the value of c is 0.33. If the value of c is 0, then we get y equals the cube root of x cubed, but the cube root of x cubed is just x, so we get y equals x, and that's why we have that diagonal line. Let's do this to, let's see. There we go. Let's do that to make it a little bit easier to see. All right, but I don't want to graph just a one solution. I want to graph multiple solutions. So what I'm going to do is I'm going to change that constant to something specific like 1, but now I'm going to copy and paste this multiple times. And we're just going to go over a whole bunch of values. For example, when the constant is 2, the graph looks like that. When the constant is 3, the graph looks like that. When the constant is 4, the graph looks like that. And I think I'm going to take this back down a notch. There we go. When the constant is 0, it's that straight line that I was telling you about. Or it can be -1. Looks like I'm kind of making an onion here. -2, -3. -4, looks like I got an extra one here, I guess we'll go with -5. And we get what's called a family of solutions to the differential equation, which again was dy dx equals x squared over y squared. Is this all of them? Not really. I'm wondering how far we can make this thing large out. Let's just throw a larger number in here. 15, 25, 125, let's zoom out for a second. So it looks like I can make this stretch out as far as I want by just making that constant larger, either positively or negatively. Right now it's 11,125, and it's way on out there. But my point is that's a graph, or graphs, a graphical representation of the solutions to the differential equation dy dx equals x squared over y squared. But I also want to look at the solutions for the one we did in the video after that, where we solved the equation dy dx equals 6x squared over 2y plus cosine of y. Let's get rid of all these. And when we solved that, we got an equation that we couldn't solve for y. The equation was y squared plus sine of y equals 2x to the third power, and see, we've already got a solution there, plus some constant. And again, we'll add a slider here to represent some unknown constant, which is currently sitting at 1. And I'm wondering what this graph will do as I activate this slider and let the value of c oscillate between -10 and 10. And by the way, you can change those parameters by clicking. For example, if I want the c to oscillate between -25 and 25, I can do that. And I can even tell it its step size or leave it alone. So let's see what happens. There's large values, and now it's going to, interesting. It's interesting that when the constant is getting large negatively, I'll slide it manually, this almost ends up looking like a vertical line, which makes me wonder if there's something to that. So I'm going to go -1000 and really go crazy with this constant and see what happens. It looks like it's getting practically vertical. Zoom out. Which makes me wonder what that constant is, where it's intersecting. It's not letting me click there. Sometimes it'll let you click on a point and see what it is. But it looks like it's about 7.93 something. I wonder if that's some magical number. And just for kicks, and this wasn't part of the video because I didn't know that was going to happen, I'm going to go back to the home perspective, and I'm going to put a really large negative number here. I'll just keep putting on zeros to see what happens. Oh, it disappeared. Where'd it go? Oh, it's over there. Okay, I'm zoomed way out. It's what I call a Google jump, like when you're on Google Earth and you jump up into the sky. It's kind of crazy. Let's go back, keep adding on zeros and see what happens here. Keeps moving over, and I'm not really sure if it gets vertical, but from a theoretical perspective, it's making me wonder why it's acting like that. But let's get out of my theoretical playground right now. Put the plus c back in there and take our constant back into a reasonable level and go back to the default zoom. Alright, so those are what the solutions of this equation look like there. And again, generally when you're representing the solutions to a differential equation's general solution, you just graph multiple versions of it with different copies of the constant, or different values of the constant. Let's put a +1 there, and then we'll copy this a few times, and then just go change the constants here. Let's go +1, +2, +3, +4, +5. Let's do a 0, and a -1, and a -2, and a -3. By the way, they don't have to be integers. You can use decimals. You can use whatever numbers you want. But I guess I'll get rid of that. But that is a graphical representation of the solutions, the second differential equation that we solved, which was 6x squared, dy dx equals 6x squared over 2y plus cosine y. Needless to say, if you were going to sketch these solutions to a differential equation, ideally you want to use technology, because sometimes equations are so complicated they're difficult to sketch by hand.